Okay, next talk is by Bentuo Zheng from University of Memphis, USA, and the title is Banach spaces with ball covering property.
Okay, thank you for the introduction, and also thank the organizers for the invitation to this beautiful place and a wonderful conference. So today I'm going to talk about the Banach spaces with the ball covering property. So the ball covering property was first studied by geometers for finite dimensional spaces, and then extended to infinite dimensional spaces by functional analysts. So, so this property is a geometric property, but very closely related to the topological property of the dual space. So let's look at the definition. So take an infinite dimensional Banach space X, and if you look at the unit sphere of the space, and if you can cover the unit sphere by countably many balls, of course not containing the origin, then we say the Banach space has the ball covering property. Okay? So if you have a uniform control of the radii of the covering balls, then we say the space has the strong ball covering property. And the covering balls may approach the origin. Okay, so if the balls can be chosen so that they are uniformly away from the origin, then the space is said to have the uniform ball covering property. Okay. All right, so of course it follows easily from the definition, every separable Banach space has all these properties, okay? So you just choose the dense subset of the unit sphere, okay? Any balls of any small positive radius would cover the unit sphere. Okay. So the first important results about the ball covering properties proven by Zheng. It says if X has the ball covering property, then the dual space is weak star separable. Okay. So a natural question is what about converse? Okay, if you add some additional conditions, say if X is locally uniformly convex and the unit ball is weak star separable for X star, then X has the ball covering property. And also if X is smooth and the ball of X star is weak star separable, you can also get X has the ball covering property. So for those results, you certainly need to add more conditions. And so the real question is still, does the weak star separability of X star implies BCP? Okay, so the following result is actually a renorming result, but it shows you that the answer to the question is no. Okay, let's look at the theorem. So if you choose any lambda between 0 and 1, then you have a renorming of little l infinity in the following way. So the first part is just the original L infinity norm, and the second part is actually the quotient norm, okay? So it's the nim-sup of the coordinates. And this lambda controls the percentage of these two norms. And if lambda is strictly greater than 1/2, then this new norm would give you the BCP space. But if lambda less than or equal to 1/2, then the new norm gives a space without the BCP. Well, so this result actually tells you that the BCP is not preserved under linear isomorphisms. However, the weak star separability is a topological condition, so it's invariant under linear isomorphisms. So this would tell you actually the answer is no, because the weak star separability is a topological property, but the BCP actually changes when you choose a different ring norm, okay? Because you choose a different lambda, choose a lambda greater than 1/2 or lambda less than 1/2. One norm has the BCP, but the other one doesn't have. So this shows you actually the answer for this question is no. All right. Okay, so, and also the result tells you that this BCP does not pass to quotient spaces, because if you look at this result, if we take lambda to be 0, if lambda is 0, then this norm is actually just this part, the lim sup of the coordinates, which is just the quotient norm over C0. So by this theorem, we can also get that this space L infinity over C0 does not have the Born covering property. So the Born covering property does not pass to quotient spaces. So a natural question is whether the Born covering property passes to subspaces. And another result shows that this little L1, 0, 1, this is a unit interval, which is a subspace of L infinity, which does not have the Born covering property, but it is easy to see little L infinity has the Born covering property. Okay, so it does not pass to subspace. Okay, so although the weak star separability of X star does not tell you the BCP of X, however, they're very closely related. The result, here is the result. If X star is weak star separable, then you can have a it's a renorming which are pretty close to the original norm, so that the new norm, under the new norm, the Banach space indeed has the BCP, okay? By a small perturbation, the space can be made to have the BCP if X star is weak star separable. However, this theorem doesn't have a control of the radius of this covering balls. Another strengthened result by Van Zankel tells you that actually, by a small perturbation of the norm, you can get the strong BCP, which tells you that the radii of the covering balls are uniformly bounded, okay? You have an even stronger result, okay? Stronger result. So this tells you the weak star separability actually very close to the BCP, And another result of Van Zankel in the same paper tells you that if you add a slightly stronger condition, that is X star has a countable R norming set, then it can be renormed to have the uniform BCP. Okay, and it follows from these two results, actually the strong BCP and the uniform BCP are different properties in general, because this condition contains a countable R norming set is strictly stronger than the weak star separability of X star, because the count example is just the Johnson-Lindenstrauss space. Okay, Johnson-Lindenstrauss space. All right, but if the Banach space has the strong Born covering property with a very good control, if the supremum of the covering balls, the radii of the covering balls is strictly less than 1, then this forces the space to be separable, okay? So if the balls can be made very small with radius less than 1, then this would conclude the X is separable. Actually, this number 1 is the best, because if you look at L infinity, you can choose a countable set of balls with radius 1, exactly 1, which covers the unit sphere of L infinity. So this result cannot be made better, okay? The best result. Okay, so of course, the first question about these three properties, the BCP, strong BCP and uniform BCP, is that whether there are different properties. Okay, in a paper with a law, we actually had a very explicit construction by taking L infinity direct sums of a sequence of spaces with the Born covering property. We showed that the three properties are actually different properties, All right. Another natural question for Banach analysis is the following. If you have two spaces with property P, so you look at the direct sum, whether the direct sum has the same property, okay? So this question was first studied by I'm sorry, I didn't put the name here. So with some additional condition, if the spaces Godot differentiable and both spaces have the Born covering property, then the sum has the Born covering property, And later on with law, we are able to remove this differentiability assumption. Actually, we prove a stronger condition, a stronger result, that is even for the infinite direct sum, the BCP is still preserved. Okay, so if you take a sequence of Banach spaces with the Ball covering property, then take the LP direct sum of the spaces, then the direct sum has the Ball covering property. This include both one and infinity. And of course, the corollary is that if X has the Ball covering property, then LP of X has the Ball covering property. So what is the next natural question? This is little LP, then what about capital LP, okay? Okay, so the question is, if you have a measurable space and look at LP of X, capital LP of X, if X has the Ball covering property, thus LP of X has the Ball covering property. But of course, you do have to pose a restriction on the measured space. It can't be too big, because this is a countable covering, okay? It can't be too big. So if you assume the measured space is separable, then the result tells you that this is indeed true. So LP of X has the BCP if and only if X has a BCP. But in this case, there's a slight difference here. The infinity case is not included. For little LP case, the infinity case is included, but here, for capital LP, this is not true. Actually, we actually showed that just capital L infinity itself fails the Ball covering property. So actually, infinity is not true for capital LP case. This also provides another proof about the BCP, which is not preserved under linear isomorphisms, because little L infinity is isomorphic to capital L infinity. However, little L infinity has a Ball covering property, but capital L infinity doesn't have it. Okay, so this is a simpler proof, okay, than the abstract proof in the earlier papers. All right, so what's next? Little LP, capital LP, then C of K. So let's look at C of K spaces. Okay, so the natural question is, okay, so we do need to find the right topological property about this, say, underlying space K, so that if X has the BCP, then CK of X has the BCP. So in the beginning, the natural guess would be if the topological space K has a countable basis, the second countable has a countable basis. However, we worked for quite some time. We found out there's always something missing there. We can't prove it. Okay, it turns out the right condition is a condition very closely related to a countable basis. This is called the weak basis, the pi basis. The pi basis is just a collection of open sets, so that every open set contains one of the elements. Okay, so this is a weak basis, but not basis. Okay, the right formulation is if K has a countable weak basis, then X has the Ball covering property if and only if CK of X has the Ball covering property. So here is the result. So let K be a locally compact Hausdorff space and X be a Banach space. So C0 of Kx has the Ball covering property if and only if both C of K and X have the Ball covering property, or K has a countable pi basis and X has the Ball covering property. Okay, so along this line, we actually go from the finite direct sum to infinite direct sum. So little LP case, capital LP case, C of K case, and well, let's look at what would be the next question. This is also natural for functional analysts, okay? You have a property for larger space. What about some class of subspaces may preserve this property? So the natural class of subspaces is the complemented subspaces of a Banach space, especially because this is a geometric property. So we would like to look at one complemented subspace, because you can make a projection not not like orthogonal or whatever like that. It should be one complement. So let X be a Banach space with the ball covering property. Y is a one complement subspace. Does Y have the ball covering property? Actually, in order to solve this problem, we work on the ball covering properties for operator spaces. So typically, it's the B of H, the space of bounding linear operators on a separable Hilbert space. Okay. So this result says that if H is a separable Hilbert space, then B of H actually has the ball covering property. Okay, this very large space has the ball covering property. And we also know that just now, capital L infinity fails the ball covering property. And we also know that capital L infinity is isometrically isomorphic to a one complemented subspace of B of H. Okay, this is the classical result. So this would tell you actually the question for the question is no, because B of H has the ball covering property, and capital infinity doesn't have the ball covering property, but it's a one complemented subspace. Actually, this is also completely one complemented, okay, in terms of the operator space language. So, well, okay, just now we said that B of H has the ball covering property. H, a separable Hilbert space, can be identified as little L2. So the natural extension would be, what about B of LP and B of C0? Okay, indeed, we prove a stronger result in this situation. So let X be a Banach space with X star separable. And for P strictly between 1 and infinity, any subspace of B from X to little LP containing the finite rank operators have the, not only the BCP, the uniform BCP, a stronger condition. So any Banach space will show that X star is separable, and any subspace containing finite rank operators would have the uniform BCP. So as a corollary, we know that every subspace of B of LP containing the finite rank operators has the uniformly bounded, uniformly ball covering property. All right, so after we finish the case for B of little LP, okay, of course, we want to look at capital LP. However, that's a place where we got stuck. Okay, we got some of the results for special case, that is the capital L1 case. Okay, the space of bounding linear operators on capital L1 actually fails the ball covering property. Okay, using a theorem we proved here. So let X and Y be Banach spaces. If B of XY has the ball covering property, then both X star and Y have the ball covering property. But you see here, the dual of L1 is L infinity, but L infinity fails the ball covering property. So this is a corollary of the theorem here. And then we proved that B of X to L infinity has the ball covering property if and only if X star has the ball covering property. And if you look at the B of X C0, this is the same. So for X star to have the ball covering property. So the corollary for this theorem is the following, okay? So if X is a norm space, then B of L1 to X star has the ball covering property if and only if X star has the ball covering property. So this would tell you that both B of L1 and B of C0 have the ball covering property, because in the theorem we just presented P strictly between 1 and infinity. Okay, in this case we cover the 1 case and the infinity case. Okay, and I'm going to finish my talk with two open questions. So the first one is this one. So whether the space of bounding linear operators on capital P has the Borel covering property. So the major difference here, okay, why we got stuck, is because for little LP we have a one unconditional basis or one symmetric basis. Okay, when you are trying to construct the approximations, the Borels, so you do use that property. However, for capital LP, although you have an unconditional basis, the hard basis, however, it's not one unconditional. You have the unconditional constant. Okay, but you cannot just do a simple renorming. Of course, you can do a renorming to make it to be a one unconditional basis, but since this is a geometric property, after renorming, you might change the property of the original space. So you can't do renorming. You have to directly go through the space. Okay, so this would be I would say, is a very interesting question, but I believe there may be some new approaches may be needed. Okay, and another question is related to what I talked about in the beginning. That is, so for every separable Banach space, it's easy to see it has the Borel covering property, strong Borel covering property, and uniformly Borel covering property. But you can't just say, okay, if the space has the Borel covering property is separable, certainly this is wrong. But so the right formulation is, if X has the Borel covering property in every equivalent norm, thus X separable. Okay, little L infinity is not the case because you have renormings. Okay, make it either with the BCP or not with the BCP. So this is the second question. Okay, the third one I didn't list is the following, because when we look at the direct sum, we only look at the little LP direct sum. You may look at the other different direct sums. For example, we considered Olich direct sums and Lorentz direct sums. But in general, what should be the right formulation is, if you take a one unconditional basis, and then you take a one unconditional direct sum of Banach spaces, whether the BCP passes from the summand to the summation. Okay, so that would be the third question. So this is the end of my talk. Thank you.
Many, many thanks for your interesting many tools. Are other question here or answer?
What is about subspaces of invertible or compact operators?
Okay, so when you talk about say compact operators, what space are you talking about? What LP?
Like LP,
for example,
LP small.
For example, for little LP, the answer is already here, right? Because any subspace contains the finite rank operators would have the BCP, right? So for some other spaces, if you say compact operators, I would say, for example, for capital LP case, we don't know, because even for the entire space.
And invertible operators, invertible.
Invertible operators, okay, so this is a good question, but I think
it's quite good
right.
for applications.
We haven't considered invertible operators, okay.
Thank you. Yeah. It's very interesting for applications, for integral equations, for instance, something. Does it relate to some applications, this property? This is quite curious.
So I think when you talk about invertible operators, I would say because you are talking about a set, right? So yeah. That's a little bit different.
Considering like open subspace in B, X, Y, for example, like invertible operators, as we know.
Yeah. So whenever you talk
like
about
subspace,
invertible operators, it's not gonna. You can make it like a linear space. So that's in a different setting. Okay, I would say you can consider maybe different subsets. That's possible, but you have to impose the right condition, because here we're talking about spaces.
Yeah. Okay. Thank you.
Okay. Let me mention your theorem about the CK of X. No? You provide that the CK of X as a...
Just a moment, let me go back to the place. Yeah.
Yeah, here. CK of X as BCP, if and only if it's CK, and X as BCP. But you know, you can rewrite the CK of X as an injective tensor product of CK and X. Then it should be natural to ask if you have two Banach spaces with BCP, then injective tensor product still has, or projective, of course.
Yeah, thank you. Actually,
have you thought about that? Or?
Yeah, actually, in that paper, because I didn't write it, for some of the results, we just passed to an injective tensor product to have the characterization go that way to trying to prove the result. Yes, we indeed would consider, but in general, because if you are away from like C of K, or C of K for injective tensor product, or L1 for projective tensor product, then things are much more complicated because those spaces are really very far away from your product, right? So it's not easy. Yeah, in the CK case, we indeed use the injective product.
Okay, but do you think in general, the projective or injective tensor product to Banach say with Banach spaces with BCP or not?
In general, our guess is difficult because if you just take arbitrary two spaces to take the injective tensor product, that space is huge.
Oh, yeah, of course, it's huge.
It's much larger, so somehow it's very difficult to directly lift the information from the base space to the larger space. Maybe you look at a particular one could work, but that...
Okay, thank you.
The same question about tensor product. It's the same.
I'll say? Okay.
Yes.
Okay, any other question? No? If not,
Paco?
Oh, Paco. Sorry.
Okay, well, what I'm going to ask you, maybe it's on the slides. Can you go back to because you showed a theorem where you prove that summation of xi, like the p summation of xi. Okay, so sequence, okay. And then after that, you also showed on a slide about hereditariness to one complemented subspaces, right? Hereditariness of like after.
Yeah. After that, we show that it doesn't pass to one complemented subset. But in this case, in LP case, it passes to LP summons.
Okay, that was my question.
It's not a general one complemented case.
Okay.
Like the capital R infinity complemented in B of H, but that complementation is actually internal direct sum.
Okay.
That's different. This is external direct sum.
Okay.
Yeah.
Okay. But can you go back to the one complex? Sorry.
So go back or forward?
I don't know exactly where it was. Okay, maybe back.
Back?
Yeah, back or no? I think it was further. Sorry, forward. Okay. Back. Okay. Yeah. That's okay. Okay. And okay, so there's another slide, sorry, about this, the hereditariness. No, this is one direction. I mean the other direction, where you showed that example where the L infinity is isometrically isomorphic to one complemented in a subspace, and then it's not like BCP is not hereditary to. Can you show that slide, please?
Okay.
Sorry. No, I think it was back.
No, not here. Let me see. Yeah, here, right?
Yes. Okay. I think it's in the previous slide to this one, you posed the question, right? About, okay, yeah, question. Yeah, that's the question. So have you tried, there are stronger one-complemented subspaces, like E-complemented, or have you tried hereditariness?
You said what complemented?
Capital E complemented is stronger. It implies one complementation and other geometrical properties related to two-dimensional norms and stuff like that.
Okay, so here,
or in general, any other complementation which is stronger than one complementation.
So in here, I just mentioned a little bit. For example, this capital L infinity is completely one complemented. So that's why in the sense of operator spaces, it's a stronger complementation.
Yeah, it's a stronger complementation.
But still fails. Still fails. So then you want to formulate what is really a stronger complementation.
There are different generalization. Well, there are different complementations which imply one complementation. There's, for example, there's this one-one complementation, but I don't think that one is going to help. That means that both both the projection and the complementary projection I minus P both are one projections, and there are other generalizations of one complementation that maybe. I mean, my general question is that it may be worth studying, trying that question for stronger definitions of one complementation. I mean, different from completely, different that the counterexample that you provided.
So for this question, I think we've thought about some of the other directions. For example, you may restrict to a certain class of spaces, okay, and certainly
and it is still
you see whether you have it. As you said, you may consider at the same time some requirement for the dual space. For example, the complementation, the original one, and the dual space. Okay, there could be such a try, but yeah, we haven't really gone very far. But certainly, that's one thing we might consider.
Okay. That was. Yeah. Thank you very much. I'm sorry for.
Maybe it's time for the last talk of this morning session. It will be. No, we thank the course.